everybody, welcome back to Measure Theoretic Probability. When we last left off, we were talking about the expected value for simple random variables, and I was about to try to convince you that it doesn't matter how your simple random variable was represented. The expectation, if you follow our new definition for expectation for simple random variables, will always give you the same thing. So I thought I should back up and talk about a little bit what I meant by how your random variable was represented. A simple random variable is a random variable x of omega that has this form. It's a sum of some finite number of terms, say n terms, where you have a coefficient x sub I times an indicator that says that omega is in a set A sub I. And for it to be a random variable, a measurable function, we do need these A sub I sets to be in the underlying sigma field curly f. Now, once you have a representation like this, the expected value for this random variable, denoted by this capital E of x, is a very similar looking sum, but we replace this indicator with the probability measure of the set being indicated. Now the problem, which you may or may not perceive as your problem, but I'm afraid some people will worry that a simple random variable can be represented in more than one way. And if you represent it one way and I represent it another way, and we both look to this as our definition of expectation, are we going to get the same thing? So let's jump in by looking at some examples. Suppose I have a space omega consisting of the real numbers in the closed interval from 0 to 1, and I have a sigma field and a probability measure, which is really not important here. Likely the sigma field is Borel sets and the probability measure is Lebesgue measure, but again, unimportant for these examples. Here is a simple random variable. X of omega is going to take points in omega and map them to either the numbers 2, 3, or 4. And as you can see here, if you get an omega that is greater than or equal to 0 and less than 1/3, you'll get the value 2. And if you have an omega that is greater than or equal to 1/3 but less than 2/3, you'll get the value 3, etc. Now I can rewrite this random variable in a slightly different way. I can use more sets. And so here you'll see that I have 2 times an indicator saying that omega is between 0 and 1/4, and another 2 saying that omega is between 1/4 and 1/3. These two intervals union together give us this interval back here. So these are exactly the same random variables. If you plug in an omega, depending on where it is in the unit interval, you'll still get 2, 3, or 4 for the same omegas. The question is, if you use the expected value definition on this versus this, will you get the same thing? So in the first case, you're going to get 2 times the probability measure of this interval plus 3 times the probability measure of this interval plus 4 times the probability measure of this interval. And in the second case, you're going to get something really similar. And again, I'm not even saying the probability measure is Lebesgue measure, but you can see down here that if you factor out this 2, you're left with the probability measure of the interval from 0 to 1/4 plus the probability measure of the interval from 1/4 to 1/3. And because these are disjoint intervals, they can be combined using finite additivity of the probability measure to give you the probability measure of the interval from 0 to 1/3, which is exactly what we have up here. So these two terms sum up to this term, and these two expectations are identical, even if the underlying representation for the simple random variables looked a little bit different, but were actually the same thing. Last time I said that these intervals here have to form a partition of omega, and then I took that back and I said we can actually have some overlap, but these intervals do need to union up to the entire omega. And I said that the reason that this was true is that x is a function taking all points in omega somewhere. And so these intervals need to union up to omega. I just wanted to point something out. What if you have a random variable that looks like this? My omega here is still the interval from 0 to 1, but it seems that I have a missing part here, that I have not covered the interval from 2/3 to 1. So it appears that I didn't partition omega with these two sets, but in actuality we did, because what happens if you plug in a number that is greater than 2/3 but less than 1 in here? Then this indicator will turn off and this indicator will turn off, and the entire thing will be 0. So this random variable is defined for all points in 0 to 1 inclusive, and this is exactly the same thing as if I wrote it out with a third term with a 0 coefficient, And now you can see I do have my partition of omega 0, 1 into 3 disjoint intervals. So taking the expectation using this formula versus this one is going to give you the same thing, because up here I'm going to get 2 times the probability measure of this set right here, plus 3 times the probability measure of this set. And when I try to do something similar down here, I'll get a third term, which will start with a 0 times the probability measure of this set. So not adding anything to the expectation. So no matter how you write it, at least from these two options, the expectation will look the same. Let's look at something even maybe a little more complicated. Consider this random variable. Now what I have going on right here, this interval and this interval have overlap, but this is okay. We can still make sense of this random variable. For example, if I plugged in the number 0.26, just a little bit above 1/4, but still below 1/3, that's going to be in this interval and this interval. So when you plug it in, both of these indicators turn on and this one turns off. So you end up with 2 times 1 plus 3 times 1, or 5. So this random variable actually takes on more values than it might appear that it takes on up here at first glance, but we can always rewrite it. And when we rewrite it, we have to consider all possible values that it's going to take on. And we basically are going through these intervals and looking for overlapping sections and pulling those out and making those overlap parts their own indicators. So if you need to, pause the video and look at this and this, but you'll see that these give you the exact same function. And this down here is what I was calling the canonical representation, meaning that we have a true partition of the omega from these sets down here, and we have distinct coefficients in front. If we didn't have distinct coefficients in front, we'd go back to the first example where 2 of the terms could be combined into one term into forming that canonical partition, where again, we have a partition with the sets and we have distinct coefficients. So you might see random variables that don't quite look like you have a partition, that have coefficients duplicated, that have overlapping intervals in the indicators, but they can always be rewritten in this quote unquote canonical way, which, as I remind you from last time, that's just my language. So if you go out looking for a canonical partition for a simple random variable, I don't think you're going to find anything. But hopefully I think it makes sense to talk about, and I'm going to use that language in this course. So if we try to apply our definition of expectation up here, we'll get 2 times the probability measure of this interval plus 3 times the probability measure of this interval plus 4 times the probability measure of this interval. And for the purpose of computing the expectation, just for one concrete example, let's assume that the probability measure is Lebesgue measure, or the length of this interval. The expectation up here is going to be 2 times 1/3 plus 3 times the length of the interval between 1/4 and 2/3, etc. And down here, we're going to get 2 times 1/4 plus 5 times, what is this going to be, 1/12, the length of this interval, etc. And stop the video if you need to and check out the expectation. But in either case, we're going to get 39/12, whether we represent the random variable this way or with the canonical partition. It doesn't matter. Our expectation for simple random variables is well defined no matter how we write this. But let's just look a little more closely. So suppose I have a random variable, a simple random variable x that takes on n values, and it has a sum that looks like this with some f sets down here. And let's assume I do have the canonical partition, or what I'm calling the canonical partition. That means that all these xi's are distinct, otherwise I could combine some terms. And it also means that each ai set is an inverse image of the point xi. So let's envision this with n equals 4. So here I've got an omega split into 4 sets, disjoint and unioning, giving us the whole omega. And so suppose every point up here in this set A1 maps to this point x1, every point in A2 maps to this x2, etc. Everything is distinct. The expectation under our new definition is going to be the sum as I goes from 1 to n, in this case n equals 4, of xi times the probability measure of a sub I. But a sub I is the inverse image of this little x sub I over here. So this is identical to the sum as I goes from 1 to n, or 4, of xi times the probability that the random variable x equals xi. So in this measure theoretic course, this is of course a shorthand for the probability measure of the set of omegas for which capital X of omega equals little xi. The set of omegas that map to little x1 is precisely the set A1. The set of omegas that map under x to x2 is precisely the set A2, etc. So this, our new definition, looks like this, which is what you've probably already come to expect for the expected value for a discrete random variable, in this case with only a finite number of terms. So it matches what we expect out of expectation, but now we're looking at it through the measure theoretic lens. We already talked through some examples about how using an alternative partition for omega to define your random variable x should not affect your expected value. So suppose I have this as my canonical representation for x, and suppose I'm claiming that x of omega is not only the sum of these 4 coefficients times the indicator of these 4 sets, or in general n, but also a sum of a different kind of, like a different representation like this. So maybe a sum as j goes from 1 to m of different coefficients yj times indicators on different sets, capital B1 through capital Bm. I did claim that the expectation using this is the same as the expectation using this, but what I want to say right now, right here, is that once you have something like this claimed, then you do have conditions kind of locked in. What do I mean by this? You can't just take any new partition, capital B1 through capital Bm. Suppose I take something that looks like this. Consider a point little omega in omega. Suppose we're looking at this point right here, which down in this picture is right here. Because this little omega up here is in capital A1, if you plug it into this function and look at this first representation, the value spit out by the random variable is going to be little x1. But because down here it's in capital B1, and this is also supposedly a representation of x, the value spit out through this representation is little y1. But these are supposed to be equal, and that forces little y1 to equal little x1. Now consider an omega over here. In this representation, it's in capital A2, and according to this, it's going to spit out the value little x2, whereas down here with this partition, it's still in capital B1, and according to this representation over here, it's going to spit out little y1. This means that little y1 has to equal x2, but we already said that little y1 has to equal x1. This forces x1 to equal x2, which was not allowed in the canonical partition. So the point is, if you have a random variable represented 2 ways, you have conditions locked in on what this partition can look like and what these coefficients can look like. And these 2 particular partitions, if this is the canonical one, give us a contradiction, because our canonical partition assumed that the little x's, the coefficients, were all distinct. In particular, something we're seeing here is that anytime one of these sets, AI, intersects with one of these sets, BJ, and that intersection is non-empty, the associated coefficients must be equal. Again, to say this, we might say that xi equals yj whenever AI intersected with bj is non-empty. And that is true for any 2 representations of simple random variables, not just these pictures in particular. And that's going to be important for us to prove that the expectations are well defined and give you the same values, depending on which representation you use. Now, just slightly more generally, but really saying the same thing, is that if you have the canonical partition, any other partition used to define x has to be a subpartition of the canonical partition. Suppose I have another partition, capital B1 through capital Bm. What I'm saying is that the B sets have to be completely contained within the A sets, because if not, so suppose you have B1 looking kind of like this, then you can make that same argument. If you grab an omega in this set omega, if it's in A1, then it has to map under X to little x1. And if it's in A2, it has to map to little x2. And if it's in A3, it has to map to little x3. And we said that little x1, little x2, and little x3 cannot be the same. But if there's another partition here with a set capital B1, that's saying that points over here, here, and here will all map to the same value, y1, but x1, x2, and x3 are not the same value, and you get that same contradiction. So this is basically what I said on the slide before, only slightly more generally. So what kind of partitions are valid? We just said that any partition that is a valid representation for your simple random variable has to be a subpartition of the canonical partition. So here again, I have a presumably canonical partition, and subpartitions are always valid partitions. We saw the very first example I did today, and we sort of saw why on the previous slide. But suppose I partition up each of these sets into their own sets. Then what I have is two representations for x. One has 4 terms in this picture, the other one has 10 terms. But I think I've said this now a couple times, so I won't drag you through this in slow motion. But this partition, if this blue part over here was originally A1, that all points in the blue part map to little x1, and the second partition is saying all points in B1 are mapping to y1, and so on. This is saying that y1 must equal y2, must equal y3, must equal x1. I think, yeah, I just said the same thing 3 different ways. But to finish that conversation, it's easy to see that both of these representations are going to give the same expectation. So one more time, if I have 2 representations, that locks in certain things about the coefficients, and both of these will give us the same expectations, because if I take the expectation using this representation, my first term is little x1 times the probability measure of A1, which is this entire blue set over here. And the first 3 terms over here are little y1 times the probability measure of B1 plus little y2, etc. y1 and y2 and y3 must all be equal and equal to x1. So if you take the first 3 terms over here from the expectation, you can factor out that common coefficient x1, and you're left with the probability measure of B1 plus the probability measure of B2 plus the probability measure of B3, and those add up to be the probability measure of A1. You can see we're just adding pieces of area over here, or you can claim that you're using finite additivity of probability measures. So I claim that it's easy to see that a subpartition will always give you the same expectation, and that was kind of the proof. I just didn't write it out formally. I have another claim for you, and that is that the expected value of x is independent of the partition used to define x. Have we already proven that? We did say that any valid partition must be a subpartition of the canonical partition, but what if we are looking at 2 partitions, neither of which is the canonical partition? So for just today, I'm going to reserve my capital AI sets for the canonical partition, but suppose that x is written in 2 ways using some BI sets and some CI sets. So B1 through Bn are forming a partition of omega, C1 through Cm are forming a partition. We just proved, although I didn't write all the steps out formally, that each of these partitions have to be subpartitions of the canonical partition. So here is maybe the canonical partition, and then the B sets might look like this, and the C sets like this. But as you can see, they're subpartitions of the original partition. So I already said that if you compute an expectation using this or this, you get the same thing. The same thing follows for this and this. Does the same thing follow for this and this? I guess, yeah, I just proved that in another way. So I guess I don't need this proof coming up, but do we skip it? Well, actually, I'm not going to skip it because I kind of already skipped. Let's do at least one formal proof today. Okay, my claim is that the expected value of x is independent of the partition used to define x, and I am assuming I have 2 partitions, and I'm not necessarily saying each is either is the canonical partition. So this means that the B's and the C's, one does not represent a subpartition of the other. We do, however, know that whenever BI intersected with CJ is non-empty, the coefficient XI has to correspond to the coefficient YJ. So we do know that for sure. And so the expected value under the BI partition is going to be the sum as I goes from 1 to n of xi times the probability measure of BI, whereas the expectation under the CJ partition is going to be the sum as j goes from 1 to m of yj times the probability measure of CJ. We want to see that these two are the same, so let's look at the first one and try to get to the next one. The sum as I goes from 1 to n of xi of the probability measure of BI. Because C1 through Cm does form a partition of omega, I can rewrite BI as the part that's intersected with C1, union with the part intersected with C2, union with the part intersected with C3, etc. A disjoint union. Some of those intersections may be empty, but again, I can write BI as a union of disjoint terms that look like BI intersected with CJ, and I can use countable additivity for a probability measure and say that this probability measure of BI is the sum as j goes from 1 to m of the probability measure of BI intersected with CJ. This, again, is finite additivity. I'm going to pull the xi into this sum, and we get what we get. So now if we start with the other representation for what I'm claiming is the expectation, we can do something very similar. And the sums would be in the other order, but they're finite sums. So I'm just going to flip the order, and ultimately we'll end up with something like this. Again, I want to show that this is equal to this. So now I want to show that this is equal to this. Let's look at these sets. We've got, a sum of n times m terms, and or maybe less. We might have some repeated coefficients, but let's just keep them all. And let's look at the ijth term. If BI intersected with CJ is empty, then the probability measure is 0. So for the ijth term here and here, we may have 0. And that will happen when, again, these intersection sets are empty. But if the intersection sets are non-empty, the probability measures still could be 0. We could have non-empty sets with probability measure 0. But no matter what the probability measure of these non-empty sets are, if BI intersected with CJ is non-empty, it does force the coefficient xi to equal yj. So looking at all the terms, this has to equal this. Again, if the ijth term, if this set has empty intersection, then those terms are both 0. And if the ijth term, this set does not have empty intersection, the coefficients are going to be identical. And so the terms are going to be the same there as well, and run through all n times m terms. And you've seen then that this is equal to this. Therefore, this is equal to this. This is the expectation under the B partition. This is the expectation under the C partition. And this proof did not use the fact that one of the partitions was a subpartition of the other. But if it was, if the, say, the C partition was a subpartition of the B partition, then when you get a term like this, the intersection of BI and CJ is just going to be CJ. So this will turn into the probability measure of CJ. And you can go. And that would be how you formally proved what I wrote down before with the sum of 4 terms with A sets and the sum of 10 terms with B sets, where I said it's easy to see. Okay, so before moving on to some actual new stuff, the last thing I want to try to convince you of is that those overlapping sets are okay. And I'm not going to do it for a general number of terms. So suppose I have a simple random variable with 3 terms. I've got like a y1, y2, y3, and sets b1, b2, b3. I'm going to draw generic sets b1, b2, b3 over here because I'm not given that they're disjoint or that one is contained within the other. I'm just going to draw them like a generic Venn diagram where I give some opportunity for overlap. If I wanted to compute the expected value of this, one thing you could do is convert it to the canonical partition. And to do that, you would end up sort of splitting up these sets into all the disjoint pieces of area. So you're going to get y1 whenever you're up here in b1, but not in b2 and not in b3. You're going to end up getting y2 whenever you are up here in b2, but not in b1 and not in b3, etc. And we can get all of these pieces of area. So if you compute the expectation using this representation up here, which is not canonical, the first term in that expectation is going to be y1 times the probability measure of b1. If you compute it using this canonical partition down here, you're going to get y1 times the probability measure of this set. And you're going to get y1 plus y2 times the probability measure of this set. And you can distribute that probability measure, so you'll get y1 times the probability measure of this set plus y2 times the probability measure of this set. And so if you put probabilities on all of these, multiply them by the coefficients, distribute all the coefficients, and collect all the y1s, you're going to be rebuilding the set B1 out of its individual disjoint pieces, and you're going to be using finite additivity of the probability measure to get the probability measure of B1 out of adding up individual probability measures of individual pieces. And so a little more like a proof. I wrote some things out, but didn't write it out very neatly. But you can trace through and find all the pieces of area. So expectation using this representation, even if there's overlap, is the same thing as the expectation using this representation. Okay, so real quick, let's talk about some properties of expectations. I'm going to prove all these properties for simple random variables simply because we don't even know how to define an expectation yet if we do not have a simple random variable. But most, I think all of these properties are going to hold for a general random variable and a general expectation, which again is not defined yet. Throughout this list of properties, I want you to assume we're using the canonical representation for our simple random variable. Again, throughout, I want you to assume there are n different sets and distinct values for our simple random variable. These AIs are distinct in partition omega. So I don't want to rewrite that at the beginning of each property. The first property, if the random variable x equals 0 almost surely, then I claim that the expected value of x is 0. So what does this mean? I think we've used this terminology maybe, but just in case, x equals 0 almost surely. Now x is a function on omega. This means that the probability measure of the set of omegas for which x of omega is 0 is 1. And x may actually take on values other than 0, but if maybe x took on the value 4, if the inverse image under x of 4, that inverse image had better have probability measure 0. So that's just what it means to have x equals 0 almost surely, and I claim that that means the expected value of x is 0. This is easy to see. We are assuming that we have n terms for our simple random variable. And so A1 is going to be defined to be all the omegas that map to 0. And then the A2 through AN are going to be everything else that, corresponding to all the other things that x can map to. If x mapped to 4, then the inverse image of 4, etc. So our simple random variable has the form 0 times the indicator that says that omega is an A1, plus a lot of other terms where every one of these sets has probability measure 0. And as we said, the probability measure of A1 is 1. So if you take the expectation, you just get this sum with the coefficients being the same, but the indicators replaced with probability measures. And this coefficient is 0, this probability measure is 1, these coefficients are whatever they are, and these probability measures are all 0. I am running out of time. I have like 8 things in this list. Let me get in one or just 2 more for today. I'm going to skip a proof. So number 2, if x is a non-negative random variable, or at least non-negative almost surely, so it might get negative, but it would be on a set of probability measure 0, then the expected value of x is greater than or equal to 0. So this one's really easy to see, again, by writing out the simple random variable as a sum of coefficients and indicators. The coefficients are all non-negative except for maybe some that are negative, but the corresponding indicator sets have probability measure 0. So when you take the expectation, easy to see by definition of that expectation for a simple random variable that you're going to get something non-negative. All right, let me get one more in and then we're going to have to call it a day. So if x is non-negative, or at least non-negative almost surely, I claim that the expected value of x being 0 would imply that x is 0 almost surely. So we can certainly have a mean of a random variable be 0 and not have the random variable be 0 because it's averaging things. And so you could be averaging positive and negative things and get the mean overall to be 0, and that doesn't mean the random variable is 0, but it does if x is non-negative, or at least non-negative almost surely. To prove this, let's write out the expectation for x as a simple random variable. We're going to get the sum as I goes from 1 to n of a sub I times the probability measure of a set a sub I. Now, if x is non-negative, then each of these is non-negative. A probability is non-negative. I have to say something else if I'm in the almost surely case, but I'm running out of time. But if each term is non-negative and this entire sum is 0, it forces the terms to all be 0 because we can't have some cancellation of positive terms and negative terms. And so if the ith term is 0, that forces either x sub I to be 0 or the probability measure of a sub I to be 0, or even both. And that means that the values that x can take on are either zero, or if they don't take on the zero value, if they take on other values, that happens on sets of probability measure zero, and that is the definition of x being zero almost surely. So I am out of time. I have more things in this list to come, and then we're going to get back to convergence kind of briefly and talk about limits of expectations. And then we're going to generalize expectations away from simple random variables to more general random variables. So hope to see you on the next one.